Hello, scientists. It's Miss Bruin back in the virtual lab talking light waves. So, we know from our last few lessons that light can be very different. It can look very different. Some lights are dim, some lights are bright, like almost blinding, right? And intense. Some lights can be colorful. So the light coming off of a light source can come in different shades, like a greenish color or a purplish color. Um, and some lights can just be plain old white. In order to discuss light energy in more of a scientific way, we have to talk about how it travels, how it moves, how it behaves. And light, much like water and sound, actually travels in waves. In order to understand how light behaves, let's review some of our wave lingo. We can use the same terms to describe light waves as we do to describe sound waves and water waves. So, scientists, the first word I'd like to revisit with you is the word crest. Now, I don't know if you remember this, but when we talked about those ocean waves, those water waves, the crest was the highest point that the wave reaches. It actually refers to the same exact thing in a light wave. So, right here, where you see my spotlight, that is the crest of the wave. Here's another crest of the wave. And if we were to continue to look at this wave travel, the next crest would probably land right here. Another term you have to know in order to understand waves is the trough. And if we travel all the way down from the crest, which is the highest point, we will find the trough, which is the lowest point on a wave. And if we continue back up, right, following this wave along its pathway, we'll find another crest. Another term you should remember from our exploration into sound waves and water waves is wavelength. And wavelength is one complete wave cycle. So if we look at our waves here, if we look at our diagram, we can measure from one crest to the next crest, right? Because that is one full wave cycle down to the trough and back up to the crest. And then the cycle starts all over again. So we know that wavelength measures how far apart each wave is. The other very important measurement when we talk about waves and describe different kinds of waves is amplitude. And the amplitude measures how high a wave is. It may be helpful to revisit what amplitude and wavelength mean for any kind of wave. So, when we talked about water waves, right, amplitude told us how high the wave was or how tall the waves were. Think back to those ocean waves. And the wavelength told us how many waves were coming or how fast they were coming. When we talked about sound, the amplitude told us how loud a sound was. The louder the sound, the greater the amplitude. And the wavelength, when we were talking about sound waves or sound energy, told us about the pitch of the sound. So the shorter the wavelength, the higher the pitch. I'm not sure if you remember that. When we talk about light, amplitude actually tells us how bright or intense the light is. And wavelength tells us the color that we are seeing. Let's go to the wave machine so you can see what I mean. So here we are at our FET wave machine. And if you get a chance, you can see this is the website. Maybe you've explored it before. It's a lot of fun, and they have all these different wave machines that you can experiment with. So you can really get a sense of what amplitude means when it comes to different kinds of waves, and also what wavelength means. And wavelength is tied in with frequency, right? Because the more often a wave comes, the shorter the wavelength. So we're going to talk a little bit about that as we experiment. So right now we have a green light being emitted from this light source. This green light is being beamed out, and we can actually see the waves coming. If I were to change the amplitude, like if I were to lower the amplitude or decrease the amplitude, watch what happens. How would you describe that change? It just got a lot more dim. And if we pull up the graph, we can see what that looks like in terms of a wave, right? Because this is the actual graph. So that white dotted line would be, let's see what it would be. That would be light at rest, which would mean darkness, right? And once we increase the amplitude, we start to see some dim light. And again, amplitude is the height of each wave, and it shows us how bright or intense the light is. Let's see what happens as I increase the amplitude all the way till the end. Whoa. You can see the change in how that light looks to our eye. It's a much brighter glow. But you can also see that the height of each wave has increased. So the amplitude shows us how bright a light is. The brighter the light, the greater the amplitude. The more dim the light, the lesser the amplitude. There's barely even a curve in those waves. So now that we've figured out what amplitude really means when it comes to light waves, now that we've seen what it really means, we're going to mess around with the frequency, which, as I said before, is very much related to wavelength. How many waves come in a certain period of time, right? How often are these waves coming? The speed of the waves. So right now, we see this green light being emitted. If I change the frequency and I increase the frequency, watch what happens to the light and watch what happens to the waves. They're coming at a much faster rate, and therefore the distance between each crest is much smaller. The wavelength is much smaller. I just changed the frequency. Now we see a blue light being emitted, and the waves have slowed down a little bit. Here, I'm going to up the amplitude and make it a little brighter so we can really see the change. And now as I change the frequency and drag it to a lower frequency, you can see the waves start to slow down and that wavelength increases. The distance between each crest of those waves spreads out a little bit because the waves are coming a little bit more slowly. Like, hopefully you understand a little more about what wavelength really means when we use it to describe light waves, and what amplitude means when we use it to describe different kinds of light waves. And next time you observe a light, or you're surrounded by a light, or you spot a light in the distance, try imagining what its wavelength might look like. Maybe you could picture its amplitude. Scientists, I'm signing off here, but we will pick the conversation back up next week when we go a little bit deeper in discussing waves.